everyone, and thanks so much for attending. I'm super excited to be here today to bring you my talk, Grafting Apple Trees. So my name is Jaron, and I'm a director of threat labs at Jamf. My team investigates a lot of the threat landscape just around finding new ways to detect malicious activity on macOS, and we've had to get creative in that manner a lot. It's a bit of a niche area, so we've had a lot of practice in this area, and we like to sometimes just share some of the research that we've been up to. This is actually a bit of a special occasion for me because normally I'm a little more geared towards maybe the threat hunting track, but over time I've built a number of different tools and partaken in a handful of different open source projects as well, and today I'm just here to share some of those free tools with you and how I went about creating those and why they exist. So again, we're here, we're going to talk a lot about process trees. And so first off, to kind of get into that, I generally talk about why process trees matter. And to explain that best, I usually give a rather Unix-specific example of the etc sudoers file being modified, right? So the etc sudoers file is a system file that controls which users are allowed to escalate to root. So knowing when it's modified is maybe something you might want to know on the system, right? But knowing that it's modified just by itself, knowing that information isn't super helpful. There's a lot of missing context, and that's into the why the file was modified, and we can answer that with the process tree, generally, not always, but usually those high-level answers are held in the process tree. So, for example, here you can see that Vim was responsible for modeling that sudoers file. Vim is a shell-based text editor. Many of us probably used it before for manually modifying files. So we know whoever modified it did it manually interacted, opened the file in a text editor, and modified it, right? It wasn't done in some automated form, probably, and we've answered that all by just looking at the process that opened it. So this is a pretty common process tree when we run into Vim. If we look further up the tree, we see that ultimately Vim was opened by a terminal, and up towards the top of the tree, this tells us that even though we know it was opened by a terminal, that doesn't, that's not groundbreaking information. This is a very normal tree, but knowing that a terminal opened Vim tells us that this was done by a user who was graphically logged in, right? You don't use a terminal under a background task or anything. A terminal is a GUI tool that you open and then run commands. So again, just adding more context comes into play as we keep looking up the process tree. Things change a little bit if we discover that the sudoers file was modified by Vim running under SSH or under the SSHD daemon. Some power users might log into a Mac, right? But it's not something most users are going to be doing, not your standard everyday user. So maybe depending on the type of system that this happened on, maybe now you're even a little more curious, just again, based on one process changing inside of that tree. Or how about a scenario where you see an MDM service, right? Jamf daemon, one of the big things Jamf does is MDM service, MDM software. So if I see something like this, I likely know that this was done via automation. This was done via some type of MDM script setup that I've set up on a server that pushes out to my fleet and runs. So at first glance, this just looking at a tree like this, I'd say, hey, that's probably some type of admin script. But if we expand siblings inside of a tree, for instance, if I found that echo command that modified the sudoers file, again, a pretty uncommon activity to happen on macOS, and we look at the siblings, we see there's a netcat entry in there, kind of interesting. Don't generally see that a lot, not from a standard user or not from an admin script. Generally, you never know. You run into a lot of stuff out there, I know. And then another sibling of that is the DNS-SD command. On macOS, this is a way to scan for other bonjour services on the network. In other words, if you enable SSH on your Mac, you're not actually, yes, you have an open port, but you're also broadcasting that to everybody else on the network. You can find other SSH servers on macOS by looking at bonjour services rather than having to do a port scan across the whole network. And I've seen attackers, when they get in macOS environments, actually use this command, and it calls out to me as a little more interesting than that I'd be surprised an admin would be doing this, let alone really needing to do this for some manner, right? So by looking at siblings of certain processes, we can also find some more answers, or rather raise some more questions during our investigation. So I'm here today to talk to you about two different projects that I've worked on over time. One is called TrueTree. This is a project I've had going for a very long time. In fact, this is kind of a reiteration on a talk I did a while ago when the way in which I could collect this information was a little bit different at the time. But TrueTree is kind of a PS tree-like tool. It is open source on GitHub, and essentially what it aims to do is walk every process on that's on the system and kind of build a tree that could help like inside an incident response scenario. There's some difficulties around that, and there's a reason why we need a tool like this on macOS, and I'll get into that here soon. The other is Sprite Tree, and I'll get into this a little bit later. This is a tool I built with some friends that uses the Apple Sprite Kit engine, or like the game engine, to kind of display process trees from captures of the endpoint security API data. So more real-time capture and analysis, and I'll get into that in a bit here. So why is it so difficult on macOS to actually build a process tree? Well, a lot of that is due to the difficulty around the architecture of the operating system. And that is mainly the process launchd. Launchd ends up creating process trees in a very one-dimensional way because its goal is to be this kind of super scheduler. So if you're not familiar with so much with the Apple ecosystem, launchd was added in 2005. It's basically meant to be this super scheduler where it could handle the booting of the operating system. It's the first process to run, process ID 1, and it goes on to basically bootstrap the entire rest of the operating system, services, daemons, agents. And this was to replace a lot of the that BSD side that Mac came in with. This was to replace a lot of the scripty stuff that BSD was doing at the time. So your cron, your @tasks, your RC scripts, everything when it came to services on the Unix side was very scripting heavy, and Apple kind of wanted to change that in some manner, and maybe also try to create one stronger way to do that instead of 50 different ways to do that. So one of the great things we got out of this change to launchd was the addition of launch daemons and agents. Basically, we as developers can create a plist launch agent that tells launchd what additional tasks to go on and perform at startup. So here you see I've started some service D. It'll run at startup like based on my launch daemon. You might hope that like when we look at a process listing or something like that, there'd be some clear indication that a plist or a launch daemon was responsible for this kind of tree, but there's not. When the system runs, when it starts up, it goes through these plists, it creates a new process, and we end up with launchd being the parent of whatever service we have created. In fact, it goes on to create almost all new processes on the operating system. So for example, here you see me, I'm in Finder, right? And I go on to open the books.app application. We would hope to see a process tree like this if we were a threat hunter, if we were looking through, if we were trying to, piece together how something occurred or how an app came into existence. We would hope to see something like this. What we would actually see is, once again, this, despite the fact that the user interacted, clicked on the app, it's just launchd ends up opening it. And that's because a IPC message is sent to launchd using various different means in the background. We have time to get into all those today, but essentially an IPC message is passed from Finder to launchd, which then goes on to open that books application. So we end up with two different processes as siblings rather than having any idea that they're attached in some way. Let's peek at one more example here. Let's just say that our user is in Safari and they're browsing around the internet and they download an application from the internet. They then launch that application from within like the Safari tab that just says downloads in the top, right? Like Safari is technically how the user opened this program, but once again, what we're gonna see is Safari has passed a message to launch D has opened the service. Again, that's very high level. There's more stuff happening under the hood, but it ultimately results in a process tree like this. So, hopefully you understand what I'm getting at. Basically, every process created on the operating system has a parent process ID of 1, aka launch D. This makes it almost pointless to actually build a process tree on macOS. This isn't helpful for threat hunting, it's not helpful for incident response, and it's nearly pointless because you could just assume that all collected processes have the parent of launch D. So how do we actually get there? On the left side here, you're seeing the process tree before. We've grabbed some additional PIDs to sort of enhance it and make it more useful. And then on the right side, you're seeing where it's a little more than just one-dimensional. We actually get some answers there, and I'll show a few more of those later on. But how do we get there? How do we build a useful process tree? Well, a great way to kind of start looking into this is the launch control command. Again, if you're not familiar, launch control lets you kind of interact with that launch D process number 1. It's a great way to go look up information about all running processes on your system. Usually when I have a question, this is kind of my go-to spot. I'll go to launch control, punch in the proc info argument, and then provide the PID that you're interested in. So you see here, basically, early on in this information, we get back the PID and the parent PID, right? Again, almost always going to be the PID followed by the parent PID of 1. So we'll walk all the running processes. We'll grab this information. Sometimes the parent PID isn't 1. You never know, and we'll grab it all. Where stuff gets more interesting, if you come down, you also see inside of this that launch D is tracking something called the responsible PID. This is not overly documented by Apple, but is picking up a little more. People are picking up more that this process is becoming useful than just the normal parent process ID. And the question there is kind of what is the responsible PID for attached to every single process? It's for a number of things, but one of the most interesting things that I think it provides us with is one of its tasks is to kind of report which processes should hold which permissions on the operating system. So, for example, many of us are familiar with the security and privacy controls in macOS. Basically, you need to go in here now, right, as of, I forget when Apple added TCC, but basically, if your app needs permission to look at the webcam, to have full disk access to any location on the disk, or to use the microphone, you have to approve that app now. And responsible PID plays a role in making sure that certain applications are allowed to do what they're supposed to do. Let me give an example of this. So here you see me trying to cat a file on my desktop, and I'm not given permission because my iTerm does not have permission to access the desktop. So you run into this a lot if you're using a terminal or you're using iTerm. You always got to go in and give yourself like full disk access or something else, right? So you see me here go into security and privacy, files and folders, and to iTerm, I give access to my desktop folder. Now we see the problems resolved, but there's still a question here. I didn't access the desktop using the terminal, right? Like I didn't access this message.txt file using the terminal. I accessed it using cat. I didn't give cat permission to do this. So how did macOS know to actually give me this permission? Well, on the top here, I'm recording processes in real time from endpoint security, and on the bottom, I run the cat command. Here we can see that when the cat command executes, right, we see that the capture happened. I get an exec event for the cat command executing. I see that has a PID of 25023, but I see that it reports a responsible PID of 24417. And if I was to look this up, I would see that this actually points to my active running terminal session. So essentially what macOS does is it checks your responsible PID. It says, hey, this is the cat command. It doesn't have permission to access the desktop, but its responsible process does. So we're going to allow it to happen. So that's the responsible PID. And again, there's a responsible PID attached to every running process on the system. Sometimes it will report itself, and that's usually when you're at the highest level of application, the highest level application inside of the process tree, at least as far back as you can go. If we look down a little bit further, we also see that LaunchD keeps track of the p-lists that it spawned this process due to. So you're not going to see that in like a process tree or anything like that, or inside Activity Monitor, but we do get a nice path to the launch daemon that caused this program to run. LaunchD is aware of that, and we can collect that information by sending a message to it and getting that information back. Yes, you can shell out and use launch control. There's also private APIs that you can call to get that information back as well. Oftentimes, when you have hit that highest level application, in other words, if I'm happen to see a ton of shell commands or something and I realize they're coming from Slack, that's great. The responsible PID would help us pinpoint that. But what happens when you hit the highest level application, like Slack, where a user opened this in some way, right? And we see here it has a PID, and we see its responsible PID matches that PID. So we have nowhere higher to go now because LaunchD is the parent. The responsible PID hasn't told us anything more useful. Like, we know Slack was opened by the user, but maybe we actually care how it was opened by the user. Maybe we don't, but sometimes you do, right? So we can actually get that answer through something called the Application Services Framework. This isn't going to last much longer. This has been deprecated for a while, but it's still working today. It's still working on Sequoia. You can't call it with Swift because it's so old and Apple won't let you do that, so you got to write some creative Objective-C code to do that. But essentially what this is if you recall Carbon, for those that actually, for it mattered to back in the day, essentially when Apple acquired Next and they were working on making Next Step, basically the new implementation, the new macOS, right? We had this macOS Classic that Apple was running and was the Apple operating system before the acquisition of Next, and then after that we had OS X, and there was this giant gap between the two because they were completely different architectures, completely different designs, and Carbon came along, and Carbon was going to allow users that already had created apps for this classic Mac OS platform and convert them, basically, or find a very simple way to run them on this new OS X that was promised to be coming out. So application services isn't part of Carbon, but it is kind of in the same vein and works with Carbon. There's a number of different functions in here. They're not documented well, and again, this is probably going to disappear pretty soon. So I'm looking for a new way to do this. But all of that to say, if you take this, you can use something called process serial numbers and get a response from LaunchD that tells you, hey, like I know the parent is this, but this is actually how this process was opened. Like whether that be through Finder or through the doc, etc. And I'll show an example of that. But basically, once we collect all these process IDs, we can kind of just run a decision tree here that builds the process tree that I've determined at least is the most useful for me. You can use any combination of these to build more useful process trees. But when I print it out in the open source tree, in the open source true tree, this is kind of the approach that I take to build that tree out. So here's just kind of an example where we can see some various processes. Again, feel free to download this and play with it yourself. You'll notice there's also network capture information in there too. That was something I snuck in there a little while ago, but any currently open network connections when you run that command will also kind of report in the tree as well. But for example, down here, you can kind of see the doc, right? And you also, I included some switches to also include hey, if you want to know where I got this information from or where we acquired this parent from, this is the one that TrueTree defaulted to go grab that information. So here under doc, you can see that I've opened both Slack and my mail.application via the doc, as where stuff that was opened through Finder will show up under Finder and etc. All right, so that's True Tree. I wanted to save a bit of time also to discuss a separate tool I created titled Sprite Tree, which is a similar idea but with more of a sandbox capture slash real-time approach, right? So Sprite Tree was a brainchild of myself and a coworker, Maggie Zernhelt, and a good friend, Matt Schott. We had a lot of fun just kind of playing around and making this. But we wanted to, do the real-time kind of capture approach. And we wanted to kind of mimic the True Tree setup. And this was for multiple different reasons. Basically, we have access at Jamf to a lot of these different PIDs and processes when we're doing different threat hunting and detection writing. And we wanted an easy way to kind of detonate malware and then look at, okay, like with all this information we collect, if we can rearrange the tree and look at it the way we want, what more detections could we write based on parent-child relationships, based on pivoting around the process tree in this manner, right? So the only thing of the True Tree side that we can't collect here is that application services framework lookup, that kind of carbon component, but otherwise the Apple Endpoint Security API returns everything else we would need to still build kind of a fun and useful tree. So here you're looking at the application. It's written purely in Swift. It actually uses Apple's SpriteKit framework, like I said, to deploy endpoint security data. We did it this way just because it allowed us to be really expandable. Really, we could come back and change any code we want. We can add new features. We didn't have to rely on, another framework. I had played with writing some applications using D3 and JavaScript and bringing those into like a macOS application. It's not fun. It's not pretty. So it was fun to kind of restart and do it in a fresh way. So just a bit about how it works. First off, its primary purpose is to take data captured from ESLogger. That's a command line tool that was added to the operating system at the start of Ventura. So any system running Ventura later, you can do this and then load the result into Sprite Tree. So essentially here, you see us calling the ESLogger commands. You're going to see the different event types we want to look for. Fork, exec, create, and rename. And finally, we're going to redirect the results of that command into just a JSON capture. And if you've worked with ES data before, you know the results are quite large. So like this is meant for smaller captures, basically small little sandbox captures that we can then load in and do some analysis on. It's not meant for like capturing data all day. You're probably going to crash something at that point. We're not quite there yet. So we're recording events after we do this. So after this, I'll open a terminal application window and we'll just plug in some random commands. Nothing overly interesting here, if I'm being honest, so I'm going to skip a little bit. But after that, we'll open a new tab. In this new tab, in this same terminal, we're going to run some additional commands as well. We'll touch like a temporary file. We'll move that temporary file. I don't know, just doing some random commands here. But let's say that we want to SSH into a computer, right? And we don't remember how. So we'll look at the man page for SSH, and now assuming that we've remembered how to use SSH, we're going to just SSH into our own local host. Again, demo purposes. I'll get into why in a second. But once we're SSH'd into our own local host, we will cat the Lord of the Rings calendar that used to exist as an Easter egg from the BSD side of macOS. No longer does. That left us 2 iterations ago. Worst mistake Apple ever made. All right, moving on. Okay, so Sprite Tree. Basically, we're going to boot up Sprite Tree. We're going to load in that capture that we just created. And we'll see that we're greeted with a process tree for events that took place. Now, by default, once you load it in, everything's loaded through just the parent and the parent-child relationship versus like trying to do a bunch of True Tree stuff, right? So, for example, here, and this is a little bit outside of what we talked about, Sprite Tree is also going to take forks and execs, and it's going to link them up accordingly. Forks are clones of processes. Execs overwrite those clones, essentially. We didn't get into that. That's a whole different ballgame. But Sprite Tree is also going to take that information. It's going to link that all up correctly. By pressing escape inside Sprite Tree, this allows you to build a a process tree by a PID of your choosing. So we'll opt for the true tree style here because that's just what I default to. So we see this actually does create a slightly more helpful tree. Maybe you couldn't tell that just by looking at those two different videos, but I assure you it does. But it's cleaner to analyze, and now we can kind of look at this. So one of the first things you'll notice is that some of these nodes have that sort of smoky effect on it. That's just for telling you, like, hey, this was a fork. In other words, it's almost always going to be the same process as its parent, because again, forks are clones, but the execs are lined up to those accordingly. So if you look at the process tree, you'll notice that the first is just some of the processes we ran in that first terminal. Don't worry a ton about that. The second is the commands that were executed in the background when we open the terminal. And then we see there's a big list of commands for the terminal itself. Sorry, I skipped over that a little bit. But let's go ahead. I've clicked on the ping node, and you notice we kind of get this highlighted tree up to back, like going all the way up the tree. A nice highlighted path, making it a little easier on the eyes. Secondly, we get a button that's kind of up at the top that says show the details. So it's not just the tree, you can also browse kind of the captured details of the event, hyphenated, because again, ES events are very large. Endpoint security data coming from Apple directly is very large, and we're just trying to keep it to the necessary details you might want. So this is just the ping command that we ran. As an analyst, you end up spending a lot of time doing these things. You select processes, you look at processes that ran, you look for the interesting command lines, right? And then once you've found some of those, or maybe some of the unique ones, you can take those and you can create detections for them moving forward. Yeah, here the benefit is we kind of get to do it in a more well-formatted tree. Let's scroll down really quickly to the other terminal tree. Notice that yeah, we saw the basic commands we executed, but out of this tree that we're looking at, inside this capture, we also see this very large sort of bash instance that's running a bunch of commands. If you recall, in our second terminal, we didn't really run any bash scripts, right? So this is just kind of interesting to spot. If we dig into this and we start looking into the full details of how this came into existence, we can actually see the full details. If we click on this bash instance, that this script actually spawned as a result of the man command, and that's because the man command is nothing more than a bash script. So it ends up, again, just spawning out a bunch of different shell scripts. We get a process for every created process in that shell script. So, and I certainly didn't know this before. So you run into interesting stuff when you're just investigating normal operating system usage. So that's just a quick crash course on moving around the tree. There's a few other bonus features. For example, you may notice in the settings menu earlier, we do have the option to color the tree by PID fields. One being the process group ID, didn't really get a ton into that, and the other being the responsible PID. So this is helpful in that it basically allows us to build a tree using a more logical tree layout while still coloring the nodes based on that responsible process ID. Think of it as a way to sort of visualize the processes that share various macOS permissions. For example, here you can see all processes run under the terminal are this salmon type color, right? Although terminal has two very large branches of commands open, we see that they all share the same responsible process, and therefore every command in this terminal is operating with the same app permissions. So in other words, the terminal app has full disk access, and therefore every process under terminal also has full disk access. Same for the webcam, microphone, etc. Once an application is open, that app should only have permissions specified by the user. Otherwise, any way to get around that would be considered a zero-day exploit around TCC. So for example, remember when we ran that SSH command to log into our own system? So this technique was used by malware, the XCS set malware. It's actually quite old at this point, but it was really interesting at the time because it was written entirely in AppleScript. Essentially, one of the things it would do is it would log into its own, the host that had compromised, it would then enable SSH and log into itself. generating a completely different tree under SSHD, right? And it did that. For instance, here you see me, there's that cat command we did to cat the Lord of the Rings calendar. And it did that because by default, back when this TCC implementation came around, SSHD was still given full disk access. So if you SSH into the computer, you could still access any file. You think about SSH, if you're using SSH, you probably need full disk access. You probably need something more than just the user's home directory, right? So Apple would say, all right, if you're SSHing in, you have full disk access by default. So the malware would get on the host, and then it would SSH into itself and inherit full disk access. And we can kind of see that represented through the colors of the tree here. So just kind of a cool technique. That's since been patched. You now manually have to say SSH requires full disk access. That was Apple's fix for that. So that's just some examples of Sprite Tree, True Tree. I just figured I'd give a quick, more hands-on example just in terms of malware, because that is primarily where we use this as well. So last month, I think it was last month, we did a blog post on some APT attacks from the DPRK. For those that are familiar, a lot of what we're seeing out of North Korea right now is the targeting of crypto companies, right? Which we had seen happening out in the wild as well. So essentially, we saw a specific LinkedIn profile that was being used. It had built rapport with a user at a crypto company. And essentially, that user, one of the common things they do is they convince the user, like, hey, you should come work for me, we'll give you a lot more money, whatever. They build rapport over LinkedIn, like over the course of time. And essentially, to that point, once they think they have enough trust, they'll send some type of, okay, hey, like, I want you to come work for me. All you got to do is complete this coding challenge, prove to me you can do it, and yeah, we'll hire you on the spot, right? So they send the coding challenge over. And within that coding challenge somewhere is embedded malware that's ultimately going to further detonate. And then usually the DPRK spends, it can be anywhere from a little bit of time to a year figuring out how to move around that company and exfil the crypto within that company. So we had taken that coding challenge that we knew had gotten sent to a victim, and we loaded it into a sandbox environment without really knowing a ton about it. And then, I'll do a couple different things here really quick. I'll flip that into the True Tree mode. And then I'm going to color by the responsible PID. Again, everything in here has the same color, which tells me everything's operating kind of with the same permissions. There's a lot going on here because this is, the reason there's so much going on here, yes, is because there's malware involved here, but also because this is Visual Studio. Visual Studio does a lot of stuff in the background on the system when it comes to shelling things out. So if we look up the tree and we kind of zoom in here, you can see that this is Electron. Visual Studio is written with Electron, right? It's kind of a way to take a JavaScript-based application or node-based application and turn it, make it usable inside of a single containerized application. It goes on to run Code Helper, but most of the stuff inside of this tree is happening under Electron. So I'm going to zoom out just a little bit here and speak to a feature I haven't spoken to yet, and that is that of the, there's also a timeline feature included here as well. So I can take that and I can sort of drag that back, and that's going to kind of reverse the processes based on when they were created. And I can adjust this to see, like, hey, like when did a lot of this activity under this tree sort of start occurring in this capture? And I wait and I see a couple different commands spawn under one of those longer branches. So basically here, these are three commands you don't generally want to see run in succession under any process for that matter. It's either bad practice or malware. But essentially we saw that this was a curl command. It's reaching out to a server. It's downloading a second stage payload called VS Code. If we go into the context side of this info, it shows us that there was a process create done by this process for Visual Studio Helper. All right, and although that blends in very nicely, Visual Studio Helper, inside of a code challenge that is based on Visual Studio, it should never be curled down if it's called Visual Studio Helper. It should not be curled out of nowhere. especially from, you might have missed it in the curl command, but it was definitely not a legitimate looking server where it came from. So anyway, all that to say, this was a C# project, and buried inside of the CS proj file. It's kind of like a config file for when the build occurs. Lodged inside that were these 3 bash commands at the very bottom of a rather large CS proj file. So inside of that, we noticed it, and anytime when the user is ready to test their code, they do the coding challenge, they hit build. As soon as they hit build, these commands run, and the second stage payload is executed. Then after it's curled down, the execute permission is added to Visual Studio Helper, and then change flags, kind of a BSD, once again rooting from the BSD side of macOS, it adds a hidden flag to the file so that it can't be spotted in the user's in the directory it downloaded it to. Then finally, like further down in the tree, again, this is all C#, and we see this running under .NET is a bash instance that then goes on to run that Visual Studio Helper. This is a malware that we call Thief Bucket. Essentially, again, it's there. It has some built-in automation around stealing the user's keychain, as well as some built-in automation looking for interesting files, as well as trying to identify wallets on the system and things like that. One other interesting timeline observation here is that after the malware runs, we see a small gap in timeline. If you saw me just drag the timeline there, we saw there was another small gap before another group of commands executes. This is due to the fact that after the user hits build, they are prompted for a password that says hey, this project requires a password in order for you to build it for whatever reason. It even grabs based on the type of project that the user is doing. If they're doing a Visual Studio coding challenge, then it uses the Visual Studio icon. It is rather smart in the way that it displays that prompt to the user. But it basically says, to build this project requires administrative privileges for this or that. It's just a kind of embedded AppleScript prompt that then returns that password in plain text to the malware, which will then, of course, elevate after that password has been verified. But that's what you see happening here, is there's basically a small gap before more processes run. That's waiting for the user to enter their password. And then once they do, the DSCL command is run. DSCL lets you kind of interact with Open Directory. It's going to let the malware verify that the password that was entered was correct. If it was correct, it'll stop prompting the user. If it was wrong, it'll just keep prompting the user until they type in the right password, right? And that's after they type in the right password is after we see more processes get created on that timeline. All right, so that's kind of the 2 different tools that I've been, spending a lot of my time on over the past few years, and a lot of the research that I've done in terms of how can we better try to find answers in a macOS process tree. Those are available at themittenmac.com. Feel free to go there, as well as you can download the tools there. That'll bring you to the True Tree open source code as well on GitHub. Sprite Tree is there. It's free to download. It's free to use. It's not open source at the moment, mostly because I just have a lot of cleaning up to do with the code. I do plan on releasing it as well. I just haven't gotten around to it yet. But the Mitten Mac is where I post different blogs and different information about some of the things I find interesting in terms of the macOS environment. But that is all I had.